In this video, I am going to use a very powerful piece of software. It's called Maple, to help us visualize what these Riemann approximations really are, and what are some of their basic properties. And now on the screen, you'll see the Maple application, and you'll see some code already typed in. Don't focus on the actual code. I'm going to go through and run each of these commands, and then kind of play around with some of the parameters there, so that we can see exactly what these Riemann sums look like and what they're doing. So let's go ahead and get started. So the first one, I'm just going to plot the basic natural log function, your ln function, and then shade a particular region. So and it's just showing a part of the graph. So right here is the graph of the function y equals the ln of x, and I'm only showing it for values of x between 1 and 5, and then I had it shaded, right? So when we talk about the area like under a curve or bounded by a curve, this is what we're talking about. And we've produced sketches that are meant to simulate this, but obviously the software does a much better job of graphing and shading and so forth, right? Okay, so suppose we wanted to approximate this area using our Riemmann approach, right? And so the next command is going to show you what the rectangles look like if we were to use 3 subintervals and a right endpoint, and it's gonna shade the area of the rectangles in pink, right? So let's see what that looks like. There we go. So we still have the curve. There is the curve. We can clearly see 3 subintervals, right? And we can see what's also nice is the right endpoint, for instance, for the first subinterval would be this x value, whatever it is. And again, I'm not going to get bogged down in the numbers and so forth. This is more a conceptual illustration of what's going on. But you can see that there's a little green dot. Hopefully you can see it right at that point of the rectangle. And it's choosing the right endpoint, finding the height of the curve at that point, and then creating the rectangle over the subinterval, and then it shades the whole thing, right? So just looking at this, you'll see that the rectangle includes more than just the area under the curve. It's including quite a bit above the curve as well, right? And then similarly does the same thing for the second interval. It goes up to the right endpoint here, creates the rectangle, shades everything, and then it completes it with this third one doing the same process. And something interesting happens in this case. Thinking back to Calc 1, we can describe the graph of the natural log of x as being an increasing function. So it's increasing over the interval 1 to 5. And because we are choosing the right endpoint of each interval, then the right, for all the values of x in this subinterval right here, the right endpoint will produce the largest possible y. So like if you just looked at this first subinterval here, the absolute max occurs at the right endpoint because the function is increasing. So therefore, you are using, when we use a right Riemann sum, we are using the largest possible y value as the height of the rectangle over that interval. And that's why it produces what we call an overestimate, right? Because the area of this small rectangle is larger than the area of this portion under the graph, right? So, and that's an important property, and it's more important when you get into area, or I should say subjects like numerical methods, where you really start to analyze, how good are these approximations, right? But if your function is increasing and you are using a right endpoint, then you are overestimating the area. So you're saying that the area is bigger than it actually is, right? Now with this example, we can go through. What's nice about the software is that I can go through and I can change these parameters on the fly. So let's say I wanted to see what it looks like if we did a left Riemann sum, and I'll use the same number of partitions. And now look what happens. Choosing the left endpoint, it's almost like we are underestimating the area, because look at what happens. Again, because the function is increasing, if you choose the left endpoint, you would now be choosing the value of x that corresponds to the absolute minimum of the function over each subinterval. So again, you'd be using the smallest possible y values to create the height of the rectangle, which is why in the first subinterval here, you actually don't see a rectangle, because the function value at that left endpoint is 0. So the height of the rectangle is 0. You don't see a pink rectangle over this interval. You only see 2. So you might say, well, we're only using 2 subintervals, but that's not true. We're using 3. It's just that one of those subintervals, they contribute a value of 0 to the Riemann approximation, right? So you can see the two rectangles here. So this would be now considered a pretty, poor underestimate, because it's not capturing any of this area or this area or this area, as opposed to when we did the right approximation, it overestimated it, right? Let's look at our third possibility. Let's look at the midpoint approximation. So I'll just go ahead and type in midpoint and just do enter, and now you can see. So, and this one's really clear. You can see for the first subinterval, it's again computing the midpoint, then computing the function value at that point, using that function value as the height of the rectangle, and then repeating that process. And then here you have the three rectangles that are used to produce the approximation. Now, for a midpoint approximation, it's a little bit harder to tell. Is it an overestimate or is it an underestimate? It's certainly not the exact area, because again, this rectangle, it's doing two things. One, it's including this portion right here that is not under the curve, and then it's excluding this portion here that is under the curve. So the question is, do these two kind of cancel out and kind of balance the over-under situation? It's tougher to tell. And again, as I mentioned earlier, in courses like numerical methods, which some of you may go on to take, you do a deeper dive into analyzing things like error and in all these different methods of approximation, right? So we can't make a nice general statement like this is over, this is under when the graph is increasing, we can do something similar for decreasing. It works out the same, and I encourage you to think about it. Draw a function that's decreasing, and then see what would happen if you choose the left or the right Riemann approximation. But yeah, so that's what the three forms would look like. Now let me ask a question. So for this same graph, natural log of x, and I'm not changing the interval, it's going to go from 1 to 5. If I wanted to improve upon this approximation, in other words, I want to make it better. If I don't change the function, which is right here, if I don't change the interval, which is right here, and whatever the method I'm using, I mean, yeah, okay, I can change this, but we just changed it, twice, right? We started with the right, and then we did the left, and then we did the midpoint. There was no, but once I've exhausted those three options, what else could I do to make this approximation better? Well, the only thing left here is the number of subintervals that we would use. So what would happen, let's say if I double this, if I made it 6, and again, we'll continue with the midpoint. I could do this for each of the other methods, but I'll just illustrate it with the midpoint method. If I made the number of partitions 6, let's see what happens. Well, now we can clearly see 6 rectangles. We can see each of those rectangles have a height that is equivalent to the function value at the midpoint of each of the intervals. So we can see the 6 midpoints here. And what happens is that over and under estimate, like those regions, they appear to be getting smaller. Well, that's good, because what that means is if these regions appear to be getting smaller, it means the error in our approximation is getting smaller, which means our approximation is becoming more and more accurate. Well, since it worked once, let's do it again. Let's double it. Let's make it 12. Let's see what it looks like. There they are. Again, I'm not going to count all 12 of them, but the 12 rectangles are there. You can trust Maple. It's pretty good at math. And then if I do, so I'm just going to continue to double it, right? And notice, again, something that's happening whenever you double the number of partitions, the delta, remember delta, which is the width of each rectangle, the delta is getting smaller. Now I'll keep doubling. I don't have to. It doesn't matter if I double or triple. I'm just doing something that's easy to explain what I'm doing, like arithmetically. And then this is what it looks like when you have 48. I'm just going to jump up to 100. All right, so almost or more than doubling, and then you can see, and if you notice, as my n is getting bigger, right, the number of partitions, the delta is getting smaller. And again, thinking back to limits, we know that means that our delta, well, it looks like delta is approaching 0. So those are two important things there. My n, I am making it bigger, bigger, and bigger, 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 and we know that means something's going to infinity. And it's affecting this other parameter, this delta, but in almost the complete opposite way. It's making our delta approach 0. Let's continue. So let's say I made this 200. And with n equals 200, you might say that's a big number. Yes, it would be a big number if you had to compute this sum by hand. You would be evaluating the function 200 times and summing and multiplying and things like that. But what's, I think from a graphical standpoint, the property that I'm trying to illustrate here is that as your n gets bigger, it's hard for you to even distinguish where one rectangle ends and where another one starts. Let's see what it looks like with 400. So with 400, yeah, I challenge you. If you were to show this image to anyone, and kind of block out what's going on and don't tell them the context in which we came up with this this plot that's in front of us, they wouldn't really see much difference between the first plot that I gave you where there were no rectangles. It was just the graph and I just filled this region. They would say it's pretty much the same. Yeah, it looks like I'm using a different, the graph of the function is a little thicker. It's a different color. And then this just happens to be a deeper blue. But you couldn't tell, again, just by looking at this, right, that there are a whole bunch. In fact, there are 400 rectangles here that approximate some particular area, right? And this is kind of the key to what we'll be doing shortly in a subsequent video, where we're going to say we need a precise definition of area, and we can phrase it in one of two ways. We can say it looks like when our and this is only 400, right? To our eye, right? To our naked eye, it looks like everything's kind of filled in. It's not really filled in. It's just that the rectangles are so tiny. The width is so small that we can't observe them physically, right? And in fact, that's kind of the concept of an infinitesimal, something that's so tiny that you can't really observe it physically, right? So I want to do another one, just not spend as much time on it, but I wanted to show you a region where part of the region is below the horizontal axis, or your x-axis, like right here, and then part is above, right? And it turns out this process works perfectly even if parts of your region, are below, and then parts are above the horizontal axis. Here's what the Riemman sum would look like in this case. So I think in this example, we're going to start with a partition of 6 subintervals, and I'll go straight to the midpoint method. And I don't want to imply that the midpoint method is somehow superior to the other methods in general, right? In some cases it might be, in others it might not be. But here we go. Here we can see the 6 rectangles, and look, 4 of them happen to be below the horizontal, and that helps us approximate this region between -2 and 2. And then the region between 2 and 4 that is above the horizontal, we're using these 2 rectangles. All of them defined by the midpoint of the subinterval, but just some are below and some are above. And if I did the same thing, maybe I'll do it a little faster. Let's say if we go up to, not 0 wouldn't work, 50 subintervals, here we go. You can see quite a few rectangles below, quite a few above, and we're getting that sense that it's like the whole region now is being filled in. Let's say I make it 100. Same thing, 200. Now, and it's kind of ironic, here I'm using just this is a parabola, just your basic parabola shifted down 4 units. And above we use the ln, and it was roughly the same number of subintervals that got it to the point where we couldn't tell the difference. So again, this is what it looks like if I use 400 subintervals. In this case, again, I can't tell now that they're rectangles, but I know they're there. They're just so tiny, I can't distinguish between them, right? And again, this is the concept that I want you to keep in mind as we go forward and come up with what is a formal definition. When we talk about area bounded by a curve, whether the curve is always above, always below, or kind of splits, like in this case where part of it is below and part of it is above, what do we really mean by the actual or the exact area? So we're going to make a big leap and go from the approximation to the exact, and those are some good things to look forward to. So hopefully you found this video illustrative of the concept of the Riemman approximation, and I'll see you in a subsequent video.